this lesson, we will consider the quantum Fourier transform. It should be noted that the meaning of the classical Fourier transform, as well as the other integral transform, such as the Laplace or Mendelian transforms, is the transition from one type of functions to another. Moreover, the solution of some problems may be much easier for transformed functions than for the original ones. And in this regard, the quantum Fourier transform is not an exception. This algorithm, as well as the Deutsch or Deutsch-Joseph algorithms considered earlier, serves as the basis for other quantum algorithms. For example, the search algorithm for the order or period of some unknown function, the Shor algorithm for factorizing numbers, or the Grover search algorithm. In mathematics, Fourier transform is generally introduced as an integral transform. In this case, the initial and final functions that participate in this transformation are continuous and integrable. However, in signal processing and computational problems, one has to deal with discrete functions, that is actually a set of points. In particular, a discrete function can be obtained from a continuous one. For example, we have some function of time, x of t, and if we take the values of the function at the initial time and at the first second, at the second and the third, and etc., then we will get sampling the values of that function x0, x1, and etc., xn minus 1. That is discrete function. The number of intervals n in this case is chosen constant. For discrete function, as well as for continuous one, there is also Fourier transform, which is also called discrete. As a result of this transform, we'll get another sample of values, that is discrete function y0, y1, etc., yn minus 1. The slide that you see shows the explicit form of the discrete Fourier transform and the inverse one, that transforms with which we can go back from the discrete function y to the discrete function x. It is clear that instead of the integral, as in the usual Fourier transform, we now have a sum with the normalization factor 1 divided by the square root of n. In fact, we have formulas that allow for all values of one sample to restore some value from another sample. The quantum Fourier transform is defined in a similar way. First of all, let's recall that the tensor product of two arbitrary vectors, this is vector 1 and here is vector 2, consists of A elements and B elements respectively, consist A multiplied by B elements. So the result is A multiplied by B elements. So result is the element of the Hilbert space H A power multiplied by B, and the dimension of this Hilbert space is obviously I multiplied by B. So consider the several qubits of H2 Hilbert space, and let's denote the tensor product of the qubits 0 of H2 and the qubit 0 from another H2 Hilbert space is the vector 1, 0, 0, 1, and we denote it as a vector 0 of the space H4, so 4 is 2 multiplied by 2. And state 0 of H2 multiplied by state 1 of the another H2 is 0, 1, 0, 0, and we denote it as the
state 1 of the H4. State 1 of H2 multiplied by state 0 of H2, this is vector 0, 0, 1, 0, could be denoted as state 2 of H4. And finally, the tensor product of the state 1 from H2 and another state 1 from H2, the vector 0, 0, 0, 1. And this is the state vector 3 of the H4. So these four vectors are elements of H4 Hilbert space, and we'll call them the computational basis of the Hilbert space.
So, in the orthonormal computational basis for n qubits, the quantum Fourier transform is defined as a linear operator acting on this basic state by the formula that you can see at the slide. Here I is the imaginary unit and k is the number of the corresponding basic states. It may seem that the sign of the exponent argument has changed in the quantum transform, unlike the classical one. In fact, it is nothing wrong here, and it is just notation features. It is accepted that for the direct quantum Fourier transform, we transform the state J, and the expression of the right is the result of this transform. As a result, for an arbitrary quantum state of psi, which is a superposition of the basic state J from 0 to n-1, taken with the coefficients xj, we can write down the following equality. The sum of j from 0 to n-1 xj multiplied by the state j is equal to the sum of the k from 0 to n-1 yk multiplied by the state k. In this equality, the amplitude of the probability yk is the classical inverse discrete transform of the amplitude x. It is easy to see that if we substitute the expression of yk into the resulting equality from the left and the right, we get the same expression. So, the formulas that we introduced for a quantum Fourier transform is compact and analogous to the classical discrete Fourier transform. Moreover, the operation of this transformation, as we shall see, is unitary. However, in order to build a switching circuit that performs a quantum Fourier transform, it will be convenient for us to rewrite the expression for it in a slightly different form.
Now, we want to obtain more convenient explicit form for quantum Fourier transform. Let's first of all assume that n equals to 2 to the power of n, where small n is a natural number, and the computational basis is the set of the vectors 0, 1, etc. to the 2n-1. The result of quantum Fourier transform, the state J, could be rewritten as a binary number. So it's J1, J2, J3, etc. And it's J1 multiplied by 2 to the power of n-1 plus J2 multiplied by 2 power of n-2 and so on to the Jn multiplied by 2 to the power of 0. And we also could introduce a binary fractions that have the form 0.001 J1, J2, J3 to Jm is J1 divided by 2 plus J2 divided by 4 plus etc. Jm divided by 2m. In this notation, quantum Fourier transform have the following form. So the J is 1 divided over the 2 to the power of n in half, sum over k from 0 to 2 to the power of n minus 1, e to the power of 2 pi I j k divided by to the power of n on the state k. And this is equal to 1 over the 2 to the power n and half, sum over the k 1 from 0 to 1 over the k 2 over 0 to 1, etc. kn over 0 to 1. The tensor product, the L from 1 to n, e to the power 2 pi I, j k L, 2 to the power of minus L to the state k L. And change the order of the tensor product operation and the summarizing. 1 over the 2 to the power of n and half, tensor product of L factors, where L is from 1 to the n, sum KL from 0 to 1, e to the power of 2 pi I j k L divided by 2 to the power of L to the state k L. And finally, it equals to 2 to the power n and half, tensor product L from 1 to n, 0, state plus e to the power of 2 pi I, j divided by 2 to the power of L, on the state 1. So this form of the Fourier transform will be more convenient to us.
Thus, we wrote down our basic states as binary numbers. We also determined how to write the phase in the form of a binary fraction. This allowed us to rewrite the result of the quantum Fourier transform in a more convenient form for us, which will allow us to proceed to the scheme of this transformation. Let us now consider a scheme that implements a quantum Fourier transform. At the input of this circuit, we apply the quantum state J, that is n qubits in the state J1, J2, etc., Jn. Further, Hadamard transform H are applied to each of these qubits, transforming the computational basis to the Hadamard basis. And then control logical element Rk are applied. After this element, the state of the controlled bit is shifted by the phase 2 pi I divided by 2 to the power of k. So, the Hadamard transform H is applied to the first qubit in the GE1 state, and then the chain of controlled transformations R2, R3, etc., Rn are applied. In this case, for the R2 transformation, the next qubit acts as the control qubit. And finally, for the last transformation of Rn, the qubit is in the Jn state. Then, a similar chain of transformations is applied for the next qubit, that is the qubit in this J2 state, but now it consists of the Hadamard transform H and the chain of controlled transformed Rk, but starting not with R2 but with R3. Then the procedure is repeated for the third qubit and so on. And at the very end, only the Hadamard transform H is applied to the qubit in the Gn state. Let's consider this procedure step by step.
And now we want to consider the scheme that implements the quantum Fourier transform. And in the input, we have n qubit string from G1 to Gn. And if we consider the qubit, for example, J1, then after the Hadamard transform of the qubit J1, system will be in the state 1 over the 2 in the power of 1/2, 0 plus e to the power of 2 pi I, 0 J1 to the state 1. And other qubits still unchanged. It is easy to show that if J1 equals to 1, then e to the power of 2 pi I 0.G1 is equals to minus 1, and if J1 equals to 0, then we obtain the result 1. So now let's perform the R2 transformation of the G1 qubit. The system will be in the state 1 over the 2 to the power of 1/2, state 0 plus e to the power of 2 pi I 0.J1 J2 on the state 1, and other qubits again are not changing. So after all our transformation, we have the system in the state 1 divided by 2 to the power of 1/2, state 0 plus e to the power of 2 pi I 0.G2 or G1, G2, etc., Gn on the state 1 on the states of other qubits. And if we do the same transforms with the qubit G2, the system will be in the state 1/2, 0 plus I 2 pi I 1.J1 to Jn, the state 1, And second qubit changes, and now it is equal to 0 plus e to the power of 2 pi I 0.22 etc. to Jn on the state 1. And the state of other qubits, J3 to Jn. If we apply all transform that's shown on the scheme with every qubit from J1 to Jn, we obtain the result that you can see on the slide.
So, one can see that at the output of the circuit we really got an expression that is very similar to the quantum Fourier transform of the state J. However, the qubits in it are arranged in the reverse order, so to complete the transformation we need to swap them using the exchange logic element. Let's recall that each such element consists of 3 quantum elements C0. After the exchange operations, as expected, we obtain the final expression for the quantum Fourier transform. Note that all elements of this scheme are reversible, which means that the quantum Fourier transform corresponds to the unitary operator, as quantum calculation requires. Let's compare the quantum Fourier transform with the classical one. The question is how many operations are required to be performed in both cases. If we look at the scheme again, we will see that we have applied n transformations to the first qubit, that is 1 Hadamard transform and n-1 phase shift, to the second qubit n-1 transform, and so on, down to the last qubit, to which we applied only 1 Hadamard transform. It turned out to be a decreasing arithmetic progression, the sum of the elements, which will be equal to the n multiplied by n plus 1 divided by 2. And besides, we still need to make approximately n½ exchange, that is 3n divided by 2 C0 operations. As a result, we can estimate the total number of operations in the quantum Fourier transform by the highest power of n, that is n to the power of 2. Note that the faster classical algorithm in this case will require approximately n multiplied by 2 to the power of n logical operations. It would seem that the great acceleration of calculation is obtained. Let's use it. However, in practice this is not possible due to the reduction postulate and measurement procedure. Therefore, the quantum Fourier transform is used in another way, and in the next lesson we will consider that case. That's all for now. Thanks for your attention.